capacitance rated, CRDT, indicates the rated capacitance of the capacitor at a specific voltage, in this case 7200 volts. It represents the nominal capacitance value that the capacitor is designed to provide under normal operating conditions. The value is given in microfarads, or UF, and in this case is 7.67 UF. The capacitance actual, CACT, is the actual capacitance measured. It is the actual capacitance value of the capacitor as measured in the field or laboratory. This value may differ slightly from the rated capacitance due to manufacturing tolerances, aging, and other factors. In this case, the capacitance actual is 7.91 UF. The deviation, dev, represents the percentage difference between the actual capacitance and the rated capacitance. It indicates how much the actual capacitance deviates from the expected value. A positive deviation means the actual capacitance is higher than the rated capacitance, while a negative deviation means it is lower. In this case, the DEV is +3, meaning that the actual capacitance is 3% higher than the rated capacitance. Serial/parallel S/P indicates the configuration of the capacitor bank, specifying how the individual capacitors are connected in the system. The notation 3/3 means the capacitor is connected in a Y, or Y, configuration with 3 capacitors in parallel. Now to elaborate further on the meanings of each one of the nameplate data components. The capacitance rated, or CRDT, is a crucial parameter that defines the expected capacitive behavior of the capacitor under standard operating conditions. It serves as a reference point for assessing the capacitor's performance and health over time. The capacitance rated is typically specified by the manufacturer and is determined through rigorous testing and quality control procedures. It is influenced by various factors, including the capacitor's physical dimensions, dielectric material, and manufacturing processes. The rated capacitance is usually measured at a specific frequency, such as 60 Hz, and at a defined ambient temperature. The capacitance actual, CACT, is the real-world capacitance value of the capacitor as measured in the field. It reflects the capacitor's true electrical characteristics at a given point in time. The capacitance actual can vary from the capacitance rated due to several reasons, including manufacturing tolerances, environmental conditions, and aging effects. Manufacturing tolerances refer to the inherent variations in the capacitor's physical and electrical properties that occur during the manufacturing process. These tolerances can result in slight deviations from the rated capacitance value. Environmental conditions, such as temperature and humidity, can also influence the capacitor's capacitance. Temperature variations can cause the dielectric material to expand or contract, leading to changes in capacitance. Similarly, humidity can affect the dielectric properties of the capacitor, resulting in variations in capacitance. Aging effects refer to the gradual degradation of the capacitor's dielectric material and other components over time. This degradation can lead to a decrease in capacitance, as well as an increase in equivalent series resistance, or ESR, and other undesirable effects. The deviation, or DEV, provides a quantitative measure of the difference between the capacitance actual and the capacitance rated. It is expressed as a percentage and indicates the extent to which the capacitor's actual capacitance deviates from its expected value. The deviation is a valuable indicator of the capacitor's health and performance. A large deviation may indicate that the capacitor is damaged, degraded, or operating outside of its specifications. Industry standards, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, specify acceptable limits for capacitance deviation. Capacitors that exceed these limits may need to be replaced or repaired to ensure a reliable operation of the electrical system. The serial/parallel, or S/P configuration indicates how the individual capacitors are connected in a capacitor bank system. The configuration can significantly affect the overall capacitance, voltage rating, and current carrying capacity of the system. The two most common configurations are series and parallel. In a series configuration, capacitors are connected end-to-end, with the positive terminal of one capacitor connected to the negative terminal of the next. The total capacitance of the series combination is less than the capacitance of the smallest individual capacitor. In a parallel configuration, capacitors are connected side by side, with all positive terminals connected together and all negative terminals connected together. The total capacitance of the parallel combination is equal to the sum of the capacitances of the individual capacitors. In a Y-O-Y configuration, 3 capacitors are connected in a star-like pattern, with one end of each capacitor connected to a common neutral point. The other ends of the capacitors are connected to the 3 phases of a 3-phase power system. The Y configuration is commonly used in power factor correction applications. The notation 3/3 indicates that the capacitor bank consists of 3 capacitors connected in parallel within each phase of the Y configuration. This configuration provides a higher overall capacitance and current carrying capacity compared to a single capacitor per phase. To determine the health of a capacitor, the measured capacitance should be within the manufacturer's specified tolerance range. A deviation outside this range may indicate a problem with the capacitor. The capacitor's equivalent series resistance, or ESR, should be low. A high ESR can indicate degradation of the capacitor's dielectric material. Visual inspection can reveal any signs of physical damage, such as bulging, leaking, or discoloration. Any signs of damage should be addressed immediately. The operating temperature should be within the manufacturer's specified range. Overheating can accelerate the degradation of the capacitor. If any issues are suspected, it is recommended to consult with a qualified electrician or capacitor expert for further evaluation and testing. For further analysis, a capacitor analyzer can be used to measure various parameters, such as capacitance, ESR, dissipation factor, and leakage current. A high dissipation factor can indicate dielectric losses within the capacitor. Elevated leakage current can indicate degradation of the dielectric material. Comparing the measured values to the manufacturer's specifications can help determine if the capacitor is functioning properly. Regular monitoring of capacitor parameters can help detect potential problems early on. This allows for timely maintenance and replacement, preventing costly downtime and equipment damage. If the actual capacitance deviates significantly from the rated capacitance, it may indicate a problem with the capacitor. For example, a capacitance that is significantly lower than the rated capacitance may indicate a loss of dielectric material or internal damage. Conversely, a capacitance that is significantly higher than the rated capacitance may indicate a short circuit or other failure. The acceptable range for capacitance deviation is typically specified by the capacitor manufacturer. Industry standards, such as those published by the IEEE, also provide guidance on acceptable capacitance deviations. In general, a deviation of plus or minus 5% is considered acceptable for most capacitors. However, some applications may require tighter tolerances. Exceeding the acceptable capacitance deviation may affect the performance of the circuit or system in which the capacitor is used. In power factor correction applications, for example, a significant deviation in capacitance can lead to under or overcorrection of the power factor, resulting in increased energy consumption and reduced system efficiency. In other applications, a significant deviation in capacitance can affect the frequency response, impedance, or timing characteristics of the circuit. This can lead to malfunctions, instability, or other undesirable effects. If the actual capacitance deviates significantly from the rated capacitance, it is important to investigate the cause of the deviation. Possible causes include manufacturing defects, environmental factors, aging effects, and external stress. Manufacturing defects can lead to variations in the capacitor's physical and electrical properties. Environmental factors, such as temperature and humidity, can affect the dielectric material and cause changes in capacitance. Aging effects can lead to degradation of the dielectric material and a decrease in capacitance over time. External stress, such as voltage surges or mechanical vibrations, can damage the capacitor and alter its capacitance. The capacitor's equivalent series resistance, or ESR, is a measure of the internal resistance of the capacitor. A high ESR can indicate degradation of the capacitor's dielectric material or other internal components. The operating temperature of the capacitor is another important factor to consider. Exceeding the maximum operating temperature can accelerate the degradation of the capacitor and reduce its lifespan. The ripple current is the alternating current that flows through the capacitor due to the alternating voltage applied across it. Exceeding the maximum ripple current rating can cause the capacitor to overheat and fail. When replacing a capacitor, it is important to select a capacitor with the same or better specifications as the original capacitor. This includes the capacitance, voltage rating, temperature rating, and ripple current rating. If a capacitor fails, it is important to determine the cause of the failure and take steps to prevent future failures. This may involve improving the cooling of the capacitor, reducing the ripple current, or selecting a higher quality capacitor. When capacitors are connected in series, the total capacitance is less than the capacitance of the smallest individual capacitor. When capacitors are connected in parallel, the total capacitance is equal to the sum of the capacitances of the individual capacitors. The voltage rating of a capacitor is the maximum voltage that can be safely applied across the capacitor. Exceeding the voltage rating can cause the capacitor to break down and fail. The temperature rating of a capacitor is the maximum temperature at which the capacitor can be safely operated. Exceeding the temperature rating can accelerate the degradation of the capacitor and reduce its lifespan. The ripple current rating of a capacitor is the maximum ripple current that can be safely passed through the capacitor. Exceeding the ripple current rating can cause the capacitor to overheat and fail. Capacitors are used in a wide variety of electrical and electronic circuits. They are used to store energy, filter signals, and improve the power factor of electrical systems. Capacitors are essential components in many modern devices and systems. There are several types of capacitors, each with its own advantages and disadvantages. Some common types of capacitors include ceramic capacitors, electrolytic capacitors, film capacitors, and tantalum capacitors. Ceramic capacitors are small, inexpensive, and have good high-frequency characteristics. Electrolytic capacitors have high capacitance values, but they are polarized and have a limited lifespan. Film capacitors have good stability and low losses. Tantalum capacitors have high capacitance values and good performance at high temperatures. The choice of capacitor type depends on the specific application requirements. When selecting a capacitor, it is important to consider the capacitance, voltage rating, temperature rating, ripple current rating, and other relevant parameters. It is also important to choose a capacitor from a reputable manufacturer. The lifespan of a capacitor depends on several factors, including the operating voltage, temperature, and ripple current. In general, capacitors have a limited lifespan and will eventually need to be replaced. Regular maintenance and inspection can help to extend the lifespan of capacitors. When capacitors are replaced, it is important to dispose of them properly. Some capacitors contain hazardous materials and should be recycled. Safety precautions should be taken when working with capacitors. Capacitors can store a significant amount of energy and can deliver a dangerous shock if mishandled. Before working with capacitors, it is important to discharge them properly. Capacitors play a crucial role in modern technology. They are used in a wide variety of applications, from power supplies to consumer electronics. Understanding the characteristics and proper use of capacitors is essential for anyone working with electrical and electronic circuits. The proper selection, installation, and maintenance of capacitors are essential for ensuring the reliable operation of electrical and electronic systems. Consulting with a qualified electrician or electrical engineer is recommended for complex capacitor applications. Capacitors are typically considered to be in good shape if their actual capacitance is within plus or minus 5% of the rated capacitance. However, this is a general guideline, and the specific tolerance range may vary depending on the manufacturer and the application. It is always recommended to refer to the manufacturer's documentation or consult with a qualified electrician for specific operational parameters and guidelines.